All right, in this lecture, we'll talk about spherical mirrors. So before we really go on to the image which is formed by spherical mirrors, we need to cover some of the terminologies. We will use some of the definitions. Although here we are trying to cover spherical mirrors, but these definitions are also valid for lenses, which we will cover in our next lecture. All right, okay, so let's say we will use center of curvature, and normally we'll denote it by letter C. So what does center of curvature means? This point that forms the center of the sphere that the mirror or lens surface lies on. Optical axis, the line connecting the centers of curvature of the lens surfaces or the center of curvature to the middle of the spherical mirror. Radius of curvature denoted by letter R, the distance from the lens or mirror surface to the center of curvature. Focal point, normally we denote by letter F. The point or points on the optical axis. This optical axis is also called sometimes central axis, halfway between the center of curvature and the mirror or lens. Rays coming into a concave mirror parallel to the optical axis or principal axis are reflected towards the focal point. This is often indicated on the ray diagram with an letter F. Focal length is small f, that's the focal length, and this is a focal point, right? This is so the distance from the lens or mirror to the focal point. Object distance will denote it by letter P here. The distance from the lens or mirror to the object, and image distance denoted by letter I, the distance from the lens or mirror to the image. And then we'll talk about the principal rays. This is important. These are very important rays, as it's called principal rays, to make image formation using lenses or mirrors. So the rays with easy to predict paths that are usually drawn in a ray diagram, parallel to the optical axis, through the focal point, and through the center of the mirror or lenses. So all these terminologies we need to keep in mind, but some of those things will get clearer as we move on to our next part of the lecture. All right, okay. So we'll talk here the types of spherical mirrors, and there are two types of spherical mirrors. One is called converging mirror, and the other one is called diverging mirror. So in both cases, if you look at this, this is the mirror. So when a converging mirror, this interior here is the reflecting surface, and outside is the coating, mirror coating, right? But to pay attention to this dotted line, so this converging mirror, or for that matter diverging mirror, is a part of the bigger sphere, bigger circle, right? So, and the center of the circle is C, and that's, if you remember in the earlier slide, that's this C is called center of curvature. So this is center of that bigger circle or bigger sphere, of which this converging mirror or diverging mirror is a part of it. So I want you to pay attention to this here. So you can draw a big circle or big sphere. Okay. Another thing we want to talk about this is a focal point, right? F is the focal length, right, which is the focal point and the center from the mirror, right? So if a ray parallel to the principal axis or central axis, so this is my central axis, parallel to that will pass through the focal point, right? And a ray which is incident passing through the center of curvature will be normal to that mirror, so this will retrace back. Anyway, we'll talk this one in little detail as we go for the ray tracing. Same thing here in the diverging mirror, a parallel ray parallel to the principal axis or central axis, when it diverges, when it's incident on that, it reflects back, and this ray, reflected ray or outgoing ray, seems to be coming from the focal point. Here, this ray, incoming ray passes through, outgoing ray passes through the focal length. Here it seems like coming from the focal length. And same thing here, if a ray is passing through the center of curvature, it will reflect back in the same direction, right? So what it means is this angle what really means is that this angle, if I draw a tangent at that point, this angle is 90 degree, or this angle is a 90 degree. That's what it means, right? Good. Let's quickly look at some of these mirrors. So again, this is my concave mirror. This is this outside of this mirror is the coating. This is my convex mirror. This side is coating. So if I have an object, let's say object P, this is my optical axis or principal axis. The rays, there are several rays are coming, and if this ray is at the focal point, all the rays after reflection becomes parallel. Or if a parallel ray is coming here, they will all focus at the focal point, right? Here we have again incident parallel rays shown by this arrowhead, and then when incident reflected rays seems to be coming from a point at the optical axis, and that point, that distance is called focal length f, right? So what is the focal point? All the parallel rays will focus at that point. Or if a ray is coming from that after reflection, they will be parallel to the optical axis. For ray tracing, we will use these spatial rays, let's say for a concave mirror, right? So we already talked in the earlier slide that if I have a parallel ray, parallel to the optic axis, this black color is parallel optic axis. Of course, this is my concave mirror. So if the ray is parallel to the optic axis, this will pass after reflection, pass through the focal point, right? Or a second case, or a ray passing through the focal point will, after reflection, will be parallel to the optic axis. So these two rays are important, or spatial rays, for ray tracing. Then the third one is that if a ray is falls at the center of the mirror, then on the spherical mirror, then this ray follows the law of reflection. And what does that mean? That angle of incidence is equal to angle of reflection that we saw for a plane mirror, which is true even for a spherical surface, for curved mirror, right? Okay. In a similar fashion, we can talk about the three sets of spatial rays for a convex mirror. So of course, this is an example of convex mirror, and I have the parallel rays incident on the convex mirror, and after reflection, so these are my reflected beams. After reflection, these rays seems to be coming from a common point, and that point is called focal point, as if they are emanating from that point, right? In other words, here, if I have a rays, incident, and if this mirror was not there, then these rays would have focused at that point, right? So these rays are directed towards the focal point, that common point, converging to the common point. Then these rays, after reflection, will be parallel to the optical axis or principal axis, right? And also the third one, which is same as the concave mirror we talked earlier, that a incident ray, this is my incident ray, after reflection, it follows the law of reflection. That means this angle of incidence is equal to angle of reflection. This principal axis being the normal at that point. All right. Okay. Couple of things we need to talk here. Let's take, we have a concave mirror, and using those ray diagram, let's say I have an object whose height is h. So let's say this is the h is the height of the object. So of course this is an extended object, this is not a point object. And if you pay attention here, this is the parallel ray. We don't have, so these are the three spatial rays we talked earlier. So this is a parallel ray, and after reflection, it must pass through the focal point of the spherical mirror. So that's one spatial ray. And the spatial ray is this one shown here. This, when incident at the center of the mirror, this will reflect back, obeying second law of reflection, right? That means this angle of incidence must be equal to this angle of reflection, right? And third ray, which passes through the focal point after reflection, will be parallel to the optic axis. So all these three rays meets here, and so just schematic we can show here. So this is the head of the object, and same way we can show this is the tail there. So let's say h prime is the height of the image, right? So we will not go the derivation here. Maybe we can do the derivation in the class, or I can probably do in another lecture. But so this is my image. So few things we need to talk. Since this is my focal point, so let's say this is f is my focal length, right? And this is my image. So distance from the mirror to the image is my letter I, this image distance, and P is, this is my object, this is the mirror, then P is my object distance. So a couple of formula we need to remember here. One is 1 divided by I, or P, let's call it, plus 1 divided by I, that must be equal to 1 over f, focal length. So 1 over object distance plus 1 over image distance is equal to 1 over f. So that's one thing. And second thing, about the lateral magnification, so m should be equal to h prime over h. So this is the lateral magnification. So if h prime and h are equal, that means there's no magnification or magnification of 1. And there's another relationship. You can see m is equal to negative I, image distance, over object distance. So these three things we need to remember, and this will be useful. Will be used for problem solving. Okay, so all right. Okay, good.